We have a mass of 3.6 kilograms. Let's write that down. Oscillating on a horizontal spring with a spring constant, K, equals 160 Newton meters. When the mass passes the equilibrium point, its speed, that's velocity, with velocities with direction, 5.2 meters per second. They want to know what's the maximum kinetic energy. So let's, for A, so A. So we have total energy of the system is a combination of the kinetic energy plus the elastic potential energy. Well, we have to think. When the mass is passing the equilibrium point, that's at x equals 0. It's not squeezing the spring yet, and it's not stretching the spring. So the spring is kind of limp, which means there's no spring energy. It's all kinetic energy, right? So we have kinetic energy is equal to, well, let's rewrite that a different way. We have total energy is equal to kinetic energy, which equals 1/2 mv squared. If we plug in our numbers, 1/2 times our mass of 3.6 times our velocity. Remember to square the velocity. A lot of people forget that. We have our maximum kinetic energy equal to 48.7 joules. B, what's the total energy? Well, we said the total energy when the spring is at the equilibrium, when this oscillating mass is passing the equilibrium point, is equal to the kinetic energy. So the total energy of the system is going to be equal to that same number, 48.7 joules. C, what's the maximum elastic potential energy? All right, so we go back to our E tot equals kinetic energy plus EPE. Where we're going to have the maximum kinetic energy is when the spring is stretched all the way or compressed all the way, which means there's no velocity, no kinetic energy. So now we have EPE max is equal to E total, and we already said that E total was 48.7, so that's our answer again, 48.7 joules. D, what's the maximum displacement? Well, maximum displacement, we're looking at x, delta x, right? Delta x is part of EPE. So when we have our maximum EPE, the spring will be squashed at its squashed or stretched to its maximum capacity. So EPE equals 1/2 kx squared. What we need to do now is get this x by itself. So we have to multiply both sides by 2. Multiplying both sides by 2, we're going to get 2 times EPE. And when we multiply this by 2, the half cancels, equals kx squared. We still don't have x by itself. X squared is multiplied by k, so we can divide both sides by k. And now we're left with x squared equals 2 EPE over k. Well, we have x squared, but we want x. So to get x by itself, we have to square root both sides. So now we're left with x equals the square root of 2 times our EPE, which we said was 48.7, over our spring constant, which is 160. And when you solve it, our displacement is going to be 0.78 meters. E, make a sketch of a mass spring oscillating system and show maximum displacement, equilibrium point, and the energies related to those points. So we want maximum displacement, equilibrium, and energy. Let's draw a picture of that. So we're going to call this x equals 0. We're going to call that the equilibrium. And at the equilibrium point, the spring really isn't compressed or stretched, so it has no spring energy. When we go ahead and stretch that spring to its maximum, now EPE at this point is going to be maxed out. And since the velocity has come to a stop temporarily, its kinetic energy at this point is 0. The mass is then going to fly back toward the equilibrium. Once it gets to the equilibrium, again, no EPE, but its velocity is maximum, so its kinetic energy is maximum at this point. Once that mass gets all the way back here and compresses the spring all the way, once again, our EPE is going to be maxed out, and the block will temporarily come to a standstill before reversing direction, so the kinetic energy is 0.